Hello Year 10, this is Miss Foster standing in this week for Mr. Beadle. He's asked me to do something with you on waves, so I thought I'd start by recapping wave properties. You'll find that this is a short lesson looking at those wave properties. I've then set you a worksheet, which I don't know if you've seen before, you may have, you may not, and then another little video that goes through the answers. If you find the questions easy, just use it to check your answers. If you find calculations more difficult, then it gives you a chance to go through the answers with me and see where you've gone wrong or help you understand how to attempt the questions. At the end of this little presentation, you'll see a slide with some suggested websites on. I'll also include those in the blurb underneath your YouTube video. Finally, I'd like you to have a go at the quiz I set so that I can have a quick look at how you're getting on and pass on to Mr. Beadle any areas that you've really understood or the areas that you need to improve on. Okay. So very quickly then, the first question is, how are waves produced? And I hope you already know that they are produced by vibrations. And these are vibrations that allow energy to be transferred from one place to another. So we've got three examples of waves here, and the question is asking, what are the difference between these types of wave? And it's just to make the point that waves come in all different media. So here we've got a wave travelling through water, sound waves travelling through the air, and laser or light rays travelling in this case also through the air. So our first definitions are understanding the difference between transverse and longitudinal waves. The first ones are transverse waves. Trans obviously means across. So transverse waves oscillate at right angles to the direction that the wave is actually travelling in. So in the little diagram at the bottom right, you can see a wave travelling through a rope. The movement of energy or the movement of the wave is from left to right, but the vibration or oscillation is at right angles up and down. Examples of transverse waves include light waves, water waves, and radio waves. The second type of wave then is longitudinal, and they oscillate in the same direction that the wave or energy is travelling in. So if we look at the diagram at the bottom of the screen now, we can see that the movement of energy is from left to right, but the vibration or oscillation is in the same direction, backwards and forwards, left, right, left, right. Sound waves are an example of longitudinal waves. The other important thing we need to know about longitudinal waves is that they need particles to travel through. Transverse waves, like light, can travel through a vacuum, such as space, but sound waves and longitudinal waves can't. They need particles that are going to compress and spread out, for example, the coil below. And then the last important point to make about waves travelling is that they are transferring energy from one place to another, but they're not transferring material. So although the energy moves, the material that vibrates doesn't. It will settle back to its original position. I'll give you an example with the ripple in the pond. When you drop the stone in, the ripple or the energy moves outwards. On the water moves up and down, but it doesn't move outwards with the wave. Otherwise, if you dropped a stone into a pond or a lake, all the water would move to the outside of the pond, and we know that doesn't happen. So these are the main wave properties that you need to know about, and these are definitions that it's worth you taking a bit of time learning and understanding. So the first is amplitude, which is given the letter A, and this is the maximum distance that the wave will move from its rest point, and it's always measured in meters. And we'll have a look at that on the graph on the next slide. Time period is defined as how much time it takes for one wave to pass. So if you're imagining that you were stood on the side of a pond and you watch one wave pass by from that ripple from the stone, and the amount of time it took for it to do that would be called the time period. The wave frequency F is the number of waves that pass per second, and is measured in hertz. Again, this definition is important when we start looking at questions. The wavelength is the length of the wave in meters, and we measure it either from peak to peak or from trough to trough. And again, that's clearer on the next slide when we look at the graph. And finally, wave speed is how fast the wave travels past us in meters per second. So again, if we imagine we're on that lake watching a ripple go past, we could do distance divided by time and find out the speed of the wave. There are two types of graph that we look at when we're talking about waves. And the first one is where the x-axis is measuring distance. Now in this case, if we have a look at the blue arrows, they're showing amplitude. And amplitude, remember, is the maximum displacement of the wave from its rest point. That black zero line on the x-axis represents the 0 point. That's the rope lying still, or the slinky lying still, or the flat water in a pond. As the wave goes past, it causes it to vibrate up and down, and the maximum distance it goes is the amplitude. So it's not from the top peak to the bottom trough, it's from that zero line, as though the wave is static, or the water is static, or the rope is static. So it's the maximum displacement. The green arrows represent wavelength. Now, wavelength is either measured from peak to peak or trough to trough, or really we're measuring it from the same point on the wave as it goes through a cycle. So if we look at the top arrows, we start at the top of the wave, it goes down below the axis and back up again, and that's one wavelength. If we look at the bottom green arrow, again we're doing one complete cycle. We're starting below the axis, we're going up through zero to the top and back down again. The middle one is again showing the length from 2 points on the cycle. So if we look at the left-hand side of that green arrow, it starts at the 0 line, goes up, back to 0, down and back to 0 again. It doesn't really matter, it's generally easier to measure from peak to peak or from trough to trough. The second type of graph can have time along the x-axis. Now, amplitude is still measured exactly the same way because it's the maximum displacement from the 0 line. Here, instead of wavelength, we're getting time period because the time it takes for one wave to pass or one oscillation to happen is called the time period. So whenever we're looking at wave graphs, we just need to check whether we've got distance or time on that x-axis. There are two equations that you need to be familiar with for the waves topic. The first one relates time period and frequency. And these two are the reciprocal of each other, and the word reciprocal in maths means 1 divided by. So time period equals 1 divided by frequency, or frequency equals 1 divided by time period. The second equation is known as the wave equation. And here we've got V equals F lambda, and that little symbol there is the Greek letter lambda, which we use for wavelength. You may not see this in a GCSE exam necessarily, but it is used at A level, so it's good to become familiar with it early. It also saves writing out wave speed equals frequency times wavelength. It's much quicker. Okay, so that's the end of my little lesson. You'll see on this section here there are 4 different video clips you could look at on YouTube, and I'm going to put these also in the blurb below this video. I'd recommend having a quick look through them and making sure you understand all of it. When you've done that, have a go at the worksheet and then use the second video to check your answers. And then finally, I'd like you to try the quiz. I look forward to seeing what you've done, and I'll be in touch with your lesson next week. Good luck.